Hi, everyone. Like they've said, my name is Varun. I'm part of the DX team at Chromatic and Storybook. So in my day job, I build tools that make UI development easier. And when I'm not building UIs, I like to build, work, and create generative art. Creative coding is sort of another term that is commonly used for this kind of work. And the idea is quite straightforward. I like to use web technologies like JavaScript, SVG, Canvas, WebGL to create visuals. A really sort of good way to think about this is sketching with code. So you want to create something, drawings, 3D animations, 2D animations, but you write code to get to that point. And today I want to share my journey through generative art. And in particular, I want to focus on one concept, noise, which I've encountered at every step of my experience with generative art. So we'll start back in the summer of 1982. This movie called Tron had just come out. It was full of some really innovative new CGI effects. And Ken Perlin, who was one of the researchers that worked on the film, he pioneered this new technique called noise, which was used to create a lot of these effects. And in fact, he went on to win an Academy Award for his work. And noise is just one of those things that is used for all kinds of stuff in the creative coding world. Everything from creating organic effects like clouds or landscapes or contours, or you can use it to distort objects or move them with much more lifelike behavior. So I've used this repeatedly in my work, and I've encountered it so many times. So let's get into and see how to use noise in sort of some of its applications. So at its core, noise is a function that takes in a whole bunch of inputs and outputs a value between 1 and -1. And the number of inputs you feed into the function changes the behavior of how the output is generated, which means sort of if you pass in one input, the output is always going to be between 1 and -1, but depending on the number of inputs you pass in, just the underlying mechanism changes. And the other sort of bit that you can do with noise functions is you can configure the actual noise generator itself. And there's two parameters for that. One is amplitude, which allows you to scale the noise output up or down. And the second one is frequency, which is sort of, you can think of it as details, or in terms of sine waves, it's sort of oscillations, so how fast or slow the wave is oscillating. And the noise output is kind of like a mixture of a sine wave and math.random. Another way to sort of think about noise is organic randomness. So on the left here, the pink ball, I'm getting a new value for new location for the ball on each frame. And you can see it just sort of bounces all around the screen and looks super weird. The yellow ball, on the other hand, it's also moving around the screen randomly and getting a new value each frame, but that value is coming through from a noise function. So even though it's moving around randomly, it just feels a little bit more lifelike. And that opens up a lot of interesting possibilities for generative art. So my starting point with noise was two-dimensional noise. So the idea is you provide two arguments into the noise function. So I started off with a grid of rectangles, and I used the XY coordinates as the input to the noise function. The output I simply mapped as a grayscale color for that rectangle. And what you get is this cloudy texture. And the organic bit you'll notice here is that the value for the noise value for one particular square is sort of related to its neighbors. It's close to what the neighboring value is. And that's sort of the starting point for noise for me. But you can do sort of really interesting things with this. You don't have to use the data as it's in its raw form. You can map it to whatever else you want to by simply using sort of a map range function where you know that the output is going to be between 1 and -1 or whatever amplitude you've set. And then you can map it to whatever new value or new range that you want. So one example of that is you can map it to a more interesting color scale, and you end up getting this cool looking plasma effect. And it doesn't need to stop there. So far I was using two-dimensional noise where the XY coordinates were the two inputs into the function. If we introduce a third input into that noise function, which is time, we can now start animating the noise. And to be honest, that animating noise is really straightforward. If you're starting with a particular dimension of noise, just go one dimension up, add time in, and you're good to go. And time in this case could be just a draw loop, could be a sort of a tween that's going from 0 to 1, whatever you want. It's just one value that is consistently changing over time. So this is kind of how I used noise a lot in the beginning. I made a lot of grid-based compositions and mapping noise to all kinds of stuff. So for example, starting with a grid of rectangles and just rotating the rectangle based on the noise value, or mapping it to a bunch of glyphs and again, sort of drawing that onto a grid, or using it to generate colors and modifying the shape of what's being rendered onto the grid. And you can sort of, the limit there is that it's kind of endless what you can do there. There's so many different applications. And again, you can animate that and you end up with some really cool looking effects. So that's kind of what I did a lot with noise in the beginning. And then I kind of encountered these things called contours. They look kind of like noise, but there's a lot of sort of clean lines that you see, these bands that appear. And I was really curious, like, how do I actually create these? They look like noise, but is it actually noise? And I did a bit of research, and what I discovered was it is in fact using noise. It's just combining noise with something called the marching squares algorithm. And what the marching squares algorithm does is it takes in that 2D noise data that you generated as the input, and then it will go through all of that data and it will create these lines where all the points on a particular line has the same value. So if you were to trace one of these loops around, the point for each loop is the coordinate for the underlying rectangle that I used as the input data. And if you look at the noise data generated for that particular rectangle, it's the same value across that entire loop. And that's what creates this contour effect. So the algorithm gives you a bunch of coordinates back as paths, which then you can render onto the screen using SVG or whatever technique that you prefer. And I actually got to use this fairly recently. For Storybook, we wanted to create one-of-a-kind thank you cards for our contributors. And we use contour imagery quite a lot in Storybook's brand. So we decided to use that as the background for each thank you card. And noise, much like other random generators, uses seed as a mechanism to sort of control the output. So in our case, we decided to use the username for the contributor as the value for the seed. And that way, when we rendered something onto the screen, it was a unique contour image for that particular user. And the whole thing was just sort of powered by SVG, and we rendered it out using in the browser and captured an image with Puppeteer. Then a couple years back, I started noticing these flow fields. I really like the look of these, and they kind of look similar to the contours, but the difference is with contours, you get those concentric circular effects, whereas with flow field, the paths are sort of flowing across the entire screen. I really, really like the look of this. And then in December 2019, I bought a pen plotter. And a pen plotter is essentially just a robotic arm. You feed it an SVG file, and the arm will just trace every single path inside that SVG file. So one of the first things I wanted to plot was these flow fields. So how do they actually work? Well, we start back at that 2D grid of noise once again. This time, instead of mapping it to color, I'm mapping it to rotation again. So the rotation for each spot is visualized here on the screen by those rectangles. So we take the noise value, map it to 0 to 360 degrees. Then you drop a bunch of particles onto the screen. So similar to other particle systems, create a bunch of particles, drop it onto the screen, and you check the angle for the starting point of that particle. Take a step, check the angle again, and take another step. So what you notice is these particles start flowing across this field. And if you track the location of each particle every frame, you can trace their path. And that's how these flow fields are generated. So if you drop a whole bunch of particles onto the screen, mix and match the different colors that are being used, you can create the final output. I rendered this out as SVG, in fact, sort of multiple layers of this. So each color was its own individual layer, and fed that into my pen plotter. And this is sort of what the final result looks like. I thought it looked pretty cool, and I've played around it with this a little bit more and created a few different fields. So you can change the the noise parameters to sort of modify the look and feel of the final plot. And most recently, I've been learning more about GL and shaders and trying to make stuff with Three.js. And not surprisingly, I encountered noise once again. The most sort of obvious application when it comes to 3D is for distorting geometry. So noise is often used to create terrains for video games. And the way that works is you start with a plane, a 3D plane, and the plane is made up of a bunch of vertices. Each vertex has an X, Y, and Z coordinate. So in this case, you take the X and Y coordinate, you feed it into the noise function, and you use that to calculate the Z dimension. And then you apply that to the 3D object, and you end up getting this sort of mesh-like effect. And again, if you play with frequency and amplitude, you can sort of get different results. At higher frequencies, you get sort of really jaggy terrain. At lower frequency, it looks more like sort of rolling hills. And you can create sort of really cool effects here too. So in case of 3D, it's quite expensive to do this kind of work in JavaScript. So generally, you end up writing some kind of shader to modify the geometry of this 3D object, usually a vertex shader when it comes to modifying geometry. These shaders run in the browser, but they're written in a language called GLSL, which has its own version of noise, but the concepts are quite similar to what you would get in JavaScript. And another sort of application of distorting geometry is these blobs. They're quite popular right now for some reason. You've likely seen them in some kind of tech demo or on CodePen. And it's a very similar idea to that terrain generator, but instead of applying it to a plane geometry, you apply distortion to a sphere. So the starting point is a sphere. You get the X, Y, and Z coordinates for each vertex, pass that into the noise function, and calculate a displacement, which then is applied radially. So the point sort of moves out radially in the sphere, and that's how you get this effect. And again, if you layer in time as the fourth parameter into the noise function, you end up creating animated versions of this. And once again, you can play with frequency and amplitude, and you can create sort of different variations. And you can see you can end up with quite a lot of variation where there's like little peaks or really large peaks, and the way it's oscillating is quite heavy too. So lots to play there. And just like vertex shaders, there's a second type of shader called fragment shader. So in this case, it's used to create textures, which can then be applied as a material to a 3D object. So I was kind of curious to see what can we do with a fragment shader? Can I apply noise there? And the answer is yeah, absolutely. So I ended up creating this piece where the core principle is quite similar to that 2D cloudy texture that I showed earlier. It's instead of using 2D coordinates, it's created using 3D coordinates of a sphere, and then mapped that texture to a color scale. And the interesting bit here is one of the steps in that color scale happens to be just completely transparent. So when the noise value hits that threshold, the material just completely disappears, and you can suddenly start seeing through the object, which is how you get this really cool effect where it just looks like the object opens up and you can see behind it. But the whole thing is just written as a noise function where you're passing in the coordinates as one of the inputs and time as the last input to animate this over time. So as you can see, noise is super utilitarian. You can do a whole bunch of stuff with it. It applies to 2D, 3D animation, distorting stuff, moving stuff around. So you're probably wondering what kind of tools I use. These days, I primarily use a generative art toolkit called Canvas Sketch. It's based around sort of HTML5 canvas. So you can write raw canvas code and create visuals with it. Or you can pair it with other libraries like Three.js or P5.js if you want to create 3D scenes or want to write shader code. And it's not really a framework. It doesn't really give you any kind of mechanisms to write the generative art code. You're mostly writing either vanilla JavaScript to manipulate a canvas or whatever Three.js and P5.js gives you. What it does give you, on the other hand, is all the tooling that's required to get you up and running, and a draw loop that is running at a particular frame rate. And then it allows you to export out your artwork as images or GIFs and videos. And you can even generate plotter files using this. So the FLOWFIELD example I showed earlier, I created that in Canvas Sketch, exported that out as SVG, and then ran that through the plotter. So I find that Noise is a really great way to get into generative art. And Canvas Sketch is a tool that I love using. I think it's quite approachable. So if you're interested, that's a great way to get into generative art too. And that's everything I had for you today. Thank you.